Unfortunately, we've been seeing a few failures of the Walletmor implant. This is not one of the failures, this is just a representative device. But I wanted to point out a couple things. One of the things that we've noticed is that most of the failures are occurring when it's placed in the knife edge of the hand, so about there. Um, we're not sure yet if it has anything to do with the actual knife edge, but that's where the majority of the failures we're seeing are being placed. So a few things about that edge of the hand. One is that on most people, it's a very difficult installation location because there's not a lot of tissue, there's a lot of muscle tension there. So getting the implant device or even getting the implantable tools like the dermal elevators and things like that into this area of the hand, that can be quite difficult. And then when it's time to actually insert the implant, there's a lot of effort that has to be taken to get it into that location versus, another location like top of the hand or even up here in the wrist area. This is probably the easiest location. The other thing that we're noticing is that when you clench your hand, you get this kind of muscle action here that creates a curve. And if it's a little bit too high in some people's hands, there's a pretty extreme curve here. And this device is a flex device. I mean, you can flex it. That's totally fine. But this chip here is the only rigid part, and that part you cannot flex. If you do try to flex it on that, it will break the encapsulation of the silicon die, and then that will compromise the connections to these outer wings, as we call them. So we did receive, out of the failures, we did receive one back. I've already analyzed it, and I didn't capture any video of that process, but we're going to kind of step through it. I have some photos, we'll step through those, and what kind of testing was done, and what I think the issue with that one device is. However, we really do need to analyze more returns because the concept design here, which is a PCB, flex PCB antenna with the chip on board, this has been used in many different implant designs from Dangerous Things, and we're only seeing this level of failures from some of the Walletmor installations. And again, one of the more unique aspects of the Walletmor device is the implant location. That's more customary because it's easier to use with terminals. So most of the other products that use this design concept are elsewhere in the body. So again, we're just going to try to go on data, but we need more data. So if there are any failures or you have a failure of a Walletmor implant, we do want to analyze that device. And it's just as important that when removing the device, it's removed carefully and hopefully without tools so that we can properly analyze it and it's not damaged in the removal process. But let's go ahead and get into it. So before we received any of these failures back for analysis, it was kind of assumed that there might be a reason to change the shape of the polymer encapsulation. This is the straight cut, which we were using. And you can see there's the PCB here, and then the chip is in the middle. And part of the reason we thought that this might be a problem is that the chip has a z-axis or a height that's higher than the PCB itself. And so the thought is that there might have been a problem with encapsulation around the chip where it wasn't being flowed properly. And we didn't have any visual indication that this was a problem, but just making assumptions based on, not having anything returned to us for analysis, I made a change to the actual shape to bow it out around this z-axis height to give the polymer a bit more chance to fully flow around this chip. Again, there's nothing that we could see visually, through analysis or anything that this was a problem, but just kind of better safe than sorry, and it wasn't really a big problem or issue to change the shape. So this is the first thing that we did before we received any kind of return that we could analyze and look for problems with. So that's kind of the first thing that we did. Eventually, though, we did receive a return to analyze, and this is what we saw. This is the device that was returned, and it had stopped functioning, and I confirmed that it could not be read. And right away you'll notice some things. So first of all, this curvature. So it was returned to us like this in a very large box. This was not a result of shipping. This device has a curvature that's kind of been imparted to it. And so, this could easily be, flattened out just by hand, but I was very careful to not impart any kind of bias in the review of it. But you'll notice a few things. So the curve, there's this damage, well, it's a little bit big, this damage right here, and that could be a result of removal. There's also damage on the other side. That also could be a part of removal or something that resulted in gripping it. But it would be kind of strange to grip it on both sides if you were trying to pull it out. But the thing that really interests me more than the curve is this area right here. And it's not really easy to see at this angle. So let's go ahead and take a different look at it. So this angle, you can see there is quite an interesting bump here on this side of the chip. That is not normal. And at first I thought there might be a problem with the encapsulation having maybe been breached or compromised in some way. But we have a vacuum fluorescein test that we can use to determine if the actual coating has been compromised. And so we did that next. I'm going to jump in to show you how that's done, but again, I don't have the actual test device, so I'm using a stand-in device to demonstrate, but this is how we do that test. So the first thing we want to check is that the encapsulation has not failed in some way and allowed moisture to enter the inside of the implantable device. So to do that, we use a fluorescein vacuum test. And essentially what we do is we take some clean filtered water and we add fluorescein drops. And fluorescein is just a UV reactive marking dye. It's actually used in injections to map out and trace blood pathways, angiograms, things like that. So we go ahead and put that in and then give it a good mix. And then we drop in the implant and then we take it over to the vacuum chamber. So here we have the implant in the water inside the vacuum chamber. And if there is any compromise in the coating, the air between the electronics and polymer will get pulled out. And that's what we want to have happen if there's a compromise. So let's take a look at the gauge here. We're approaching 30 inches of mercury vacuum. We're going to want it to be at 30 inches. But then, that'll be basically maximum vacuum. And then all that air, if there's a compromise, will be pulled out of that space. And when we let the air rush back in, it will force fluorescein dye water into those spaces through the compromised polymer. If there's no compromise, then there won't be any actual fluorescein pushed in, and we'll be able to see that under UV light. So we're nearly at 30 inches of vacuum. And we can see there's bubbles forming on the actual fluorescein water. This does happen. You're degassing the actual fluid. So we're well past what's necessary in terms of vacuum to pull out any air that might be trapped in the device due to any kind of encapsulation problems. So we're going to go ahead and release the pressure. And now you will be seeing those bubbles disappear, and air pressure should be forcing the fluorinated water fluorescein dye into any cracks, crevices, or encapsulation failures. And we're going to go take it out and look at it under UV light. So I want to be pretty clear, this is not a failed device. This is an example device that we didn't ship because it has some issues with the connections there. But essentially what you would do is you turn on the UV light and you'd look for any sign of fluorination, any kind of, you can see on my fingers there's some stuff, there's some marker there that I got on my thumb, but we're not seeing any infiltration or fluorination. I mean, you can see that's what it would look like, this bright green. We're not seeing anything like that. So this encapsulation is fine. So having passed the vacuum fluorescein test, I wanted to take a very close look. So I peeled back the polymer encapsulation. So this is a destructive test, but it was necessary to find out what is going on or what had happened. And right away I noticed something. The chip itself in this area is cracked, it's broken. So this black material is potting. So what this looks like overall as a chip is that you have these metal wings on the sides, and those metal wings are the contact points. So this is where the antenna is connected to the chip. But the chip itself is actually a small silicon die. It's a tiny little silicon, piece of material with the circuit lithographed onto it. I'll see if I can pull up a picture of what that looks like without this black potting encapsulation. So this is what these chips look like when they're fully packaged in a ribbon. And you can see you have the wings and you have the little potted areas, and that's where the chip goes. But let's take a look at what it looks like without the potting material. So this is what those chips look like before the potting material is added. And you can see there's the silicon die here. It's just a flat slab of silicon crystal with the circuit lithographed onto it. And there are these little pads, these little kind of silvery areas on either side. And the pads can be anywhere, but essentially one of those pads is linked to this side of the wing, and one of the other pads is linked to this side. Those pads are the contactless pads where the antenna should be connected. So these little links are called wire bonds. They're very small, and they are, essentially like a hair's width. And so those just connect, not usually all the way out to the wings, actually. Let's go ahead and remove that. They just connect over to this bus. So this is a bus that's on the side of the chip. And then this connection is cut when the chip is punched out. So this center, square is essentially floating in the potting material. And the potting material extends all the way to include the bus itself. But these tiny little hair-like wires go through that potting material. And the potting material protects them from getting broken. And then this bus area connects to the wings with these little metal, you can see this one has 3, but on the Walletmor chip, there are only 2 of these little links that connect this bus to the wing. And so that's how this looks when there's no potting material. So the important part here, let's go back and remove all this stuff. The important part here is that these little hair-like metal wires, they're wire bonded, they're fragile. And so you need to protect them with the potting material, and it's very easy to break them. And that's the important factor here. So let's go back and take a look at the Walletmor chip. So you can see in the Walletmor chip that's broken, here is the bus, and the potting material is broken away. So something has occurred, and you can't really see it in this photo, but essentially this wing here is beveled up. So it kind of comes up to a point at these little cross links here between the bus and the wing. So it looks as though this has been compressed or bent severely enough to break the potting material around the bus connection, and also create a bend or a crease right along this line. So this line is creased upward, and you can kind of see it's come away a bit from the PCB right about there. So this is what has caused the polymer to bump up. And when I remove the polymer, I could see very clearly, okay, so something has occurred to create this kind of severe bend. And really, that kind of damage to this chip area would require quite a severe bend. So severe, in fact, that I don't think it was possible to do once installed. I think it may have had something to do with the installation, whereas again, as I talked about, the tissue on the side of the hand being very difficult to work with, and if an installer is going to grab one end, like maybe this end, and then try to push it in to the tissue this direction, there's a possibility that any kind of interference or friction or anything that's encountered, you're going to increase force to try to push it in, and it may have buckled. It may have buckled momentarily or temporarily, or just enough to cause a crack. And this particular device was working for a time and then stopped working. And so if that was the case, if during installation there was enough force created to buckle the PCB and create this kind of crease here and crack the potting material, then it would have put the very small and very fine wire bond connection to the actual silicon die inside at risk. It would have basically meant that over time, if there was any additional flexing or any additional problems with movement or anything, it could just wear that wire out, or indeed, sever it eventually. And you can kind of see also right about here, there's a crack line and then another crack line here in the potting material. So whatever happened was quite severe, in fact, and enough to create this kind of buckling or rippling, not only here, but also these crack lines. So, looking at it even further, I was able to remove the actual center area by just bending it a little bit, and the whole entire area came away from the bus and the wing. And so I don't have any photos of that, but essentially it was clear that the entire potting area, this floating platform that the silicon die is on, was fairly well detached from this side, this metal wing. It was still securely attached to this side, so it bent up and away, leaving this metal wing and then just the floating bus here with nothing attached to it. So in my opinion, I think there was something that happened either just after installation or possibly during installation that caused the damage here. So that's the important analysis. But again, the amount of failures that we're seeing is going up, which is kind of concerning. So we want to be sure that we're able to analyze further failures and determine where the problem lies. If the problem is really related to damage to the chips, then we need to address it in a few ways. We need to address the installation procedure, we need to address the installation location, and we need to address potentially stiffening up or shoring up the entire antenna structure a bit, maybe making it slightly thicker or putting in stiffeners into the area just around the chip, maybe just extending that a bit beyond the chip. So again, we need more returns to be able to analyze what the failure mode might be and how to address it.